Welcome to Lecture 2 of Multidisciplinary Design Optimization. Today we will talk about the fundamentals of optimization. And before we get started, I would like to briefly review what we talked about last time. Last time we defined the concept of design optimization as seeking the best design within available means. And in that sentence, there are three ingredients that I would like to emphasize. One of them is that design optimization is a search process. It is about finding a design according to some criterion that is related to an idea of best. And you do that within your available means. That means that you do your search on a specified design space and you try to satisfy design requirements which are mathematically expressed as constraints. A multidisciplinary design optimization is a design optimization with the difference that several disciplines are involved. So, for example, when you think of a multidisciplinary design optimization process in aerospace, you could think of a structural engineer trying to optimize the structure such that loads at the wing root are minimized, and therefore he or she would try to make wings rather small, whereas an engineer responsible for the aerodynamic properties of an airplane would try to maximize the aspect ratio of a wing. An engineer responsible for fuel efficiency would try to maximize the bypass ratio of your engine, or somebody responsible for the airplane properties that are particularly relevant for your customers, the airlines, would, for example, try to maximize the diameter of your fuselage in order to increase the number of seats for passengers. So you have different disciplines involved, which may pursue different design goals, and in particular, and that's the interesting part also for us, they use different simulation models to produce numbers for their quantities of interest, and they need to be integrated in a multidisciplinary design process. And let me also tell you about one little design optimization that we performed for this class. We heard that the audio quality was really bad last time, so we optimized audio quality now within our available means by using this little microphone, and I hope now you can hear me better. We also talked about the general problem statement of design optimization, and let's briefly go through this. So we typically want to be very clear about what we actually want to accomplish in a design process, and to be as clear as possible, we use a particular formalism. And this is not only important for communication, but it is also important to feed it into a computer program, because typically algorithms or computer programs have standardized interfaces, and as long as you know what your optimization expression is and your constraint functions are and your constraints, it'll be fairly easy to operate standard algorithms. So in the beginning of your general problem statement, you want to specify what is to be minimized, and you want to express that using the so-called objective function. The objective function is a mapping from your design variables onto one scalar quantity of interest. Within that statement, you want to include what design variables are your optimization degrees of freedom. So what design variables the optimization algorithm can change in order to improve the value for your objective function. You also want to specify constraints, and there are two types of constraints. One of them are equality constraints that are expressed using an equality constraint function. And there are also inequality constraints that are expressed using an inequality constraint function. And you also include into your problem statement lower and upper bounds for your design variables. The reason for that we will talk about today in more detail. Please make sure that you distinguish between a constraint and a constraint function. These are two different things. The objective function and the constraint functions are mappings from design variables onto quantities of interest. We'll talk more about this in the end of the lecture. So then I would like to go through some notions that we will be using within this class. So typically you describe the behavior of a system, which is in our context, of course, mostly some engineering system, and even more specifically here in this class it'll be mostly structural mechanics, and you describe that behavior using so-called system equations. And from these system equations you extract a solution, and that solution represents the system response or the system responses. And again, from these system responses you extract your quantities of interest, which you will feed into your problem statement. And they are used in two places. One of them is the optimization statement about what needs to be minimized or maximized, and you do that using your you express that using your objective function. And the second place is for quantities of interest is when you formulate constraints on your optimization problem. And we also introduced this compact notation that tells you what the design variable is that will affect quantities of interest and what the optimization procedure is supposed to do with these quantities of interest. So in this case here, y1 would have to be minimized. Therefore, the mapping from x to y1 would have to be the objective function. And the other quantities of interest would be subject to constraints. For example, an equality or an inequality constraint. To be a little more specific, let's look at this example again. This was a one-dimensional rod subject to a horizontal force, making the structure undergo horizontal displacements. So this would be the system. These are the system equations, a differential equation or an expression for the total mass. This would be the system responses, a solution to differential equations, or if it's not the differential equation, the system equation, then just the same expression again. From that, again, you would extract quantities of interest like the displacement of your rod tip. And in this case, trivially, just the mass again. And using these quantities of interest, you're able to formulate an optimization problem using an objective function, in this case, your displacement, and a constraint on your mass, in this case, expressed by a equality constraint function. We will talk in this lecture about fundamentals of optimization before we'll cover more advanced subjects in the lecture to follow. And in particular, we have two chapters. One of them is on general problem formulation, and the second one will be on the characteristics of optimization problems. And the overall theme for today is from the engineering problem to the design optimization problem. So that means how to translate something that the engineer wants to have solved into something an algorithm can solve for you. We will explain our concepts in an inductive way. That means we will look at very particular cases and then extrapolate from there, making general statements. Okay, and that particular use case that we will be using a lot in this class is the so-called two-bar truss. A two-bar truss is a truss consisting of two rods that are connected by joints. And these joints, of course, cannot support any moments. So there'll be only longitudinal forces in your rods. And this two-bar truss structure is parameterized by or described by an angle alpha, by a reference rod length L. And there'll be also material parameters included that describe the material behavior. So the possible design variables that we have available would be the cross-sectional areas of the two rods, Young's modulus, the density of the material, the reference length, and the angle alpha. The system equations that we mentioned previously are in particular the balance equations at point C. Balance refers here to the balance of linear momentum, and perhaps I'm not going to go through the equations in detail, just one brief comment on this notation here. We use as spatial coordinates C and eta just to distinguish it from x. Okay, x is used for our design variables, and spatial coordinates are there for C and eta. And when you want to solve for the section forces that are active in those rods, you're going to look at the force balance in the x direction, or in the c direction, excuse me. You're going to look at the force balance in the eta direction, and can deduce from that that those two section forces S1 and S2 are F over sine alpha or minus F over tangent of alpha. For the description of the system behavior, you also need so-called constitutive equations. Constitutive equations are equations that typically express material behavior. So on a micro scale, you would relate, for example, in linear elasticity, stress and strain by Hooke's law. That would be a simple constitutive equation. On a larger scale, so on the rod scale, you could relate the deformation of the rod to the force acting by, well, what you could consider as a constitutive equation for a rod. It just tells you if you extend the length of a rod by delta L1, you would have to use this force, or this section force S1. And to use F, what we did is we plugged in this expression here into this formula. So this way we can relate the extension of those rods directly to the force acting on the node C. So we need a third type of equations in order to have a complete system descriptions, and those are the compatibility conditions, or more general relations between kinematic quantities that would tell you, for example, that the node C, the displacement of node C is equal to the extension of rod number 2, the displacement in the C direction. And the displacement in the eta direction would be this expression here. And using these equations, you come up with the same number of equations as the number of unknowns, and you can solve for it. Which we're not going to do here in this class because I'm sure you did that before in mechanics classes. The system response is the A or the solution of the system equations. So we distinguish here between A and the, because A could mean that there are several solutions available, and the refers to a unique solution of the system equations. In this particular case, actually, there is only one solution. There is a unique solution. This includes all displacements and section forces, so everything that you would solve for. And if you used a more detailed model, you could even consider the entire displacement field of your rod, parameterized by an internal variable S, which would be a variable telling you what particle of the rod to look at. So you could even solve for the entire displacement field in each bar. However, we are only interested in the deformation of the tip of the rod. So this is again to say that for your optimization problem, you typically want to condense the system response and extract the quantities of interest from it. Only those quantities that are relevant for you. And for us, the relevant quantities of interest would be the displacement of the rod tip and the mass of the two bar truss. And here's the mathematical expression for it, and also an expression for the total mass. Now let's look at the first engineering problem. It says, find the optimum angle for the best stiffness, that is minimum displacement. Well, best stiffness here implies that best is always the highest or largest stiffness. And we restrict ourselves right now as alpha to be a design variable. So we assume the perspective that alpha is something we can change, that we are in control of. And that's why we will explicitly make that the design variable, that the optimization procedure also knows that this is something that can be changed. And we express our objective function as the mapping from alpha to our quantity of interest u, which is this expression. Oh, and for one simplification, we set the two cross-sectional areas, we set them to be equal, and we define a nominal state for those design variables that we're not going to change with by these values here. And we can turn this engineering problem now into our mathematical problem statement that would read like this. Minimize f of alpha, and here you can see a short form of our previously introduced notation where we omit the degree of freedom of the optimization, and we can do that only if it's really crystal clear what it would be. In this case, we make the design variable here explicit as argument, and that's why we can do it. Okay, so writing it like this would tell you, yes, the design variable or the degree of freedom for the optimization process is alpha and nothing else. Now, let's have a brief look at the shape of our objective functions. If we plot this, we notice that in a range from 0 to 90 degrees, we will get a positive response. So starting from something that is pretty big, the displacement would become smaller and smaller and then increase again. And when you think about it, at an angle of 0 degrees, displacements would be very large, because there is almost no no resistance against deformation if you make these rods very close to each other. Well, upon increasing alpha, the stiffness of the structure, of course, would become larger, therefore the displacement would become smaller. Increasing alpha further would have the effect that this rod 1 would become larger and larger and larger, and the larger a rod, the less stiff it will be. Saying that in the limit when you approach 90 degrees, the rod will become infinitely large, and therefore the stiffness would approach 0, and equivalently the displacement would blow up. When we go beyond 90 degrees, something strange happens. All of a sudden we have a negative displacement. And that's weird, because you could imagine a, let me draw this. You could imagine the rod 1 going like this and being, for example, attached here. And it wouldn't make sense for the displacement to become negative. So there's something strange going on here. And now for our further analysis, we have two options. We can either say, well, let's ignore this and just let's restrict our analysis to the region where it seems to work, which is this one. So we have a plausible explanation for what's going on, and there's no obvious reason why this should be wrong. Or we ensure that the formula is correct everywhere to identify potential troublemakers. So there could be something in the formula that does not make it only wrong here, but also here. And I would strongly recommend to you, if you have a more complicated optimization problem where you cannot easily look at plots of your objective function like this, you should definitely try to eliminate everything that looks fishy. Because when you use optimization schemes that will explore high-dimensional and very non-intuitive design spaces, there will be a lot going on that you're not in control of. And you want to put all your energy into making sure that the optimization algorithm is doing the right thing, or the model you're using is correct. So if you encounter something like this, you should try to eliminate it. It should make sense to you why this displacement is negative. And this is what we're going to do right now in this lecture. It turns out that we have a little error in our model. And it took us a little while to figure it out, but now we found it. And I like this error so much that I thought we'd better present it in this lecture, because this is a good occasion to stress this point, that you should make sure that you understand everything about your simulation model before you start the big machinery and things happen that you're not in control of. So where's the problem? The problem is here. When we looked at this expression, so at some point you need to express your displacement, the vertical displacement of your node Z, as something that depends on the extension of the two rods. And when you do that for an angle less than 90 degrees, the relationship between delta L1 and L is just simply L1 equals L over cosine alpha. However, when your alpha becomes larger than 90 degrees, L1 would become negative, and that doesn't make sense. So the correct expression should be L1 equals L over absolute value of cosine alpha. And if you use that, you in fact come up with this expression. Or an expression that would be correct for both cases, alpha below 90 degrees and alpha above 90 degrees, and that would be this here. If you plug that in to your objective function, you'll come up with a solution that looks like this, and that makes a lot more sense. Okay, so incidentally, in this part of the design space from 0 to 90 degrees, the corrected and the not corrected formula deliver the same value. So it's actually enough to use the original formula and restrict it, constrain it to this range from 0 to 90 degrees. And that's actually what we're going to do. But as I said, I strongly recommend to make sure that you understand your objective function entirely. So the way we'll proceed is we specify lower and upper bounds for the design variable, which is 0 and 90 degrees, and move on. The design problem looks now like this. We have a design variable x equals alpha. We have our formula for the objective function that depends on the design variable alpha. And now we have an upper and a lower bound that we will treat as a constraint on the problem. And this is what we are trying to solve. Mathematically speaking, we have our objective function now expressed in terms of alpha with some constant before in front of it. And well, as you know from your high school math, the optimal solution will be at a position where the first order derivative vanishes and also the curvature is positive. The curvature is expressed as the second order derivative. Both of these conditions here are together sufficient for this to be an optimum. The gradient vanishing is a necessary condition. The gradient being equal to 0 by itself is not sufficient. Only together with the condition on the curvature being larger than 0 will provide a sufficient condition for optimality. So this is what you know from high school math. I'm not going to elaborate further on this. But let's go on and look on another design problem. The design problem to look at here is now that we changed, it's similar to what we looked at before, but the important difference is now that we change design variables. Yeah, so we include alpha as a parameter into our nominal state. Alpha is fixed at 45 degrees, and now let's change A and the cross-sectional area of both rods in order to improve stiffness. The formula for the objective function will stay the same, but now it's a mapping from A to U, the displacement of the of node C. And let's look at a design space that is given as A running from 0 to infinity. Well, strictly speaking, we have no practical limitation really of the design space. The mathematical problem statement then would look like this. It says minimize f of A, and now with a design space from 0 to plus infinity. And well, it turns out that the stiffness of the structure can be increased further and further by increasing A, meaning that the displacement U will be decreased further and further upon increasing A. And unless A assumes the value of infinity, you will always be able to find a yet better value for A in order to improve your solution. So strictly speaking, the problem does not have a well-formulated solution because A equals infinity is not an appropriate solution. And we call this optimization problem not well constrained, or actually it is ill-posed, a notion that we will talk about later. And we can fix this by introducing a constraint on a quantity of interest. So we saw for the optimization problem, the 1D problem number 2, we saw that you can constrain your problem directly by constraints on design variables. But here we're doing it differently. We're going to formulate a constraint on the quantity of interest, in this particular case, the mass. So let's look at the optimization problem again. We have a design variable which is called A, the cross-sectional area. This is our objective function, still the same, but now we explicitly formulate constraints on quantities of interest, and well, this will be our inequality constraint function m minus m naught, which evaluates is this expression here. And well, the way we formulated it is this way, is that we can apply the condition that it should be less or equal to 0, just to express it in a standardized form. And simultaneously, actually, we're going to consider we're considering right now two problems simultaneously, one of them with an inequality constraint and one of them with an equality constraint. And for this, we take the same mathematical expression. So the equality constraint function is the same as the inequality constraint function, but here we use that, of course, to formulate an equality constraint. And our reference mass, that it should be the reference mass that the value of which the total mass should assume is 2.86 kilograms. And again, we specify a nominal state for all those variables that we do not change. Now let's look at the first of the two constrained 1D optimization problems, the one with the inequality constraint. And the mathematical optimization problem now reads: minimize f of a subject to total mass minus critical mass should be less or equal to 0, and an expression that defines the design space. And when we visualize the inequality constraint as a barrier here on this plot, with the cross-sectional area on the x-axis and the displacement on the y-axis, and the objective function being represented here as the blue line, then you can easily understand that the optimum is located right on the boundary. This kind of optimum we call a boundary optimum as opposed to an interior optimum, and you can call this problem now well constrained. The constraints are such that there is no way for the solution to go to infinity. Another property of this problem is actually now that it is well posed, a term that we will also talk about a little later in this lecture. A boundary optimum does not necessarily satisfy the condition that the first order derivative is 0. And boundary optima are typically what you will encounter in realistic technical problems. So when I learned about that, I was actually a little disappointed, because I always thought that this property of interior optima, the first derivative being 0, I found that somehow beautiful, and then understanding that in most technical problems you're stuck at the boundary where this is not the case. I found that, yeah, a quite sobering experience, but this is how it is. At least the optimization problems that I encountered during my technical career, they typically had solutions on boundaries. And this is why constraint treatment is really important in optimization. So now let's look at the second optimization problem that was formulated with an equality constraint. And the expressions here are all the same, except that we replaced G by an H, because H is the name for, or the symbol for, our equality constraint functions. And now we have an equal sign here to express an equality constraint. And the solution that we encounter is trivial, but I'd like to go through it anyway, just for the reason to be complete, and also that you can follow the arguments and the language that we're using here. So essentially what we are saying is, please find the smallest possible displacement value by varying A, subject to the constraint that A should actually be equal to 150 square millimeters. So the obvious solution is that our optimum is here. And that is trivial, and in particular, it is the same solution as in the previous case. And boundary optima also have the property that they are the solution to equality constraint problems. So you could think, well, why not make life easy and solve equality constraint problems? Well, the problem is that you don't know before whether or not you will end up at the boundary, or you even may know that you will end up at the boundary, but you don't know at which boundary you will end up. And that's why, unfortunately, you would still have to solve inequality constraint problems. And again, of course, the first order derivative of this optimum is at the same location, and the first order derivative of the objective function, of course, is not 0. Now let's become one step more complex. So remember, we started with one variable, one quantity of interest. Then we added a quantity of interest when we used that for constraint formulation. And now we are adding one design variable. And the engineering problem that we're considering right now reads, find the optimum cross-sectional areas A1 and A2 for best stiffness, which is equivalent to looking for a minimum displacement with constraint mass. And again, we're going to treat this as two different problems, one with an equality and one with an equality constraint. The design variables now are A1 and A2, so we have a two-dimensional design variable vector, and the objective function becomes a little longer, and we need to have A1 and A2 explicitly available in this function. And the treatment of constraints will just be the same, just that our constraint functions also depend explicitly now on A1 and A2. So here in the case of for G, and exactly the same for H. So the functions themselves are actually the same. However, they're used in different conditions. One of them being an inequality constraint, and the other one being an equality constraint. And here is the set of reference values that hasn't changed that we'll be using for the analysis of this problem. The treatment of the first problem with an inequality constraint looks like this. The mathematical expression would read minimize f of a1 and a2 and now subject to our inequality constraint explicitly depending on two design variables. And we are going to construct our solution at first by looking at this particular diagram. So this diagram is different from what we saw in the one-dimensional case. Here we have two design variables on the x and y axes. And here you can see contour lines of the objective function expressing or showing points or lines of equal value of the objective function. And the negative gradient of f points in this direction. And this is where our preferable designs will be. So we're trying to minimize f, so we want to follow the negative gradient. And again, the inequality constraints now are visualized here by the green line. And what we call the feasible domain, that is the one that is enclosed by our inequality constraints, is this triangle. And the optimum would be again at the boundary, which you can tell by looking at the contour lines. You know, it's always going downhill, so you want to go further and further this direction. And when do you stop? When you hit the boundary, which will be right there. And the exact numerical values can be computed using numerical optimization, which we're not doing yet, but by visual inspection, you can see that it's plausible that our optimum will be somewhere here. And what is also interesting is that now the total displacement is less than what we obtained previously when we had only one design variable, because when you have more than one design variable, you can adjust more finely the location of your optimum. So having a1 equal to a2, you can only move along this line here. Then your optimum will be here. And now we can readjust both design variables such that we can also move along this line, obtaining a better solution. Now, similarly to what we did in the one-dimensional case, we will look at the second type problem with an equality constraint, and which will turn into a mathematical problem statement like this. Minimize f of a1 and a2, and now subject to exactly the same expression, only that it evaluates a 0, which means that a solution needs to be selected from this line. So it's similar to the one-dimensional equality constraint optimization problem, where there was only one point that was feasible, and that automatically, of course, is the optimum. Now we have an infinite number of points that are confined to this line here. And among those points, we need to find the one that is best, and that actually will be exactly at the same location as where the boundary optimum of the inequality constraint problem was. Why? That's easy to argue. If the equality constraint problem had a solution that was somewhere else, then the inequality constraint problem would have found that too, because it is within the feasible domain of the inequality constraint problem too. So therefore, they have to be at the same location, the optimum of the inequality and the equality constraint problem, because the solution of the inequality constraint problem is a boundary optimum. The problem that we just analyzed, the solution to a problem formulated with an equality constraint and the solution to the problem formulated with an inequality constraint happen to be the same. But this is typically not the case. It is just the case in the two-bar truss problem. And I'm going to show you an example here. It's a made-up example where this is not the case. So think of an objective function with contour lines that look like this, and the negative gradient showing toward the smallest value of the objective function, which would be located here. And if this smallest value of the objective function is located inside the feasible region and not at the boundary, then the optimum would be different for a formulation with inequality constraints than from a formulation with equality constraints. Here you can see the optimum lying on the line that represents the equality constraint, and due to this equality constraint, of course, you could not minimize your objective function any further. You would have to stay on that line, and in this particular example, the two solutions would be different. We are concluding the first chapter. In the next lecture, actually in 2 lectures from now, what you saw today, we will formulate for arbitrary number of dimensions. So today was just the prelude to warm up. Now let's talk about general characteristics of optimization problems that we can already talk about using these simple formalisms that we've seen so far. I would like to talk about these notions: well-posedness, convexity, linearity, monotonicity, continuous and discrete problems, and also about problems with closed form solutions and problems that you would have to solve numerically. Let's get started with well-posedness for our general problem statement. Well-posedness says that your optimization problem has a unique solution. So there are 2 things included: its existence and uniqueness. So if your optimization problem produces multiple solutions, it's not well-posed. If your solution problem has no solution, it's not well-posed. One example of a problem that has no solution is the optimization problem, the unconstrained optimization problem, where we use the cross-sectional area as a design variable, because the design space was not properly bound and the objective function was monotonically decreasing. That produced a scenario where, upon increasing your cross-sectional area even further, you would minimize your objective function also even further, without any boundary. And in a mathematically sloppy way, you could say the optimum is at infinity, but since that is not a proper location or a valid specification of a design, this counts as there is no solution. Okay. Another scenario where no solution exists is a scenario with an objective function that looks like this, with respect to some design variable, let's say L, on an open set. Open set means that the boundary itself is not included in the set of permissible design variable values. But all other values are. So whenever you go a little bit to the right of that boundary point, that's a permissible value. But you could move arbitrarily close to that boundary value, but not get on the boundary. And for the optimization process, that means you can approach that point further and further and further, but the point itself is not included. So there is no way to mathematically express the optimum of this, or the minimum of this problem, and therefore the optimization problem would not be well posed. This is a little artificial or theoretical example, and thank God that's not to be encountered really in practical design problems. So typically in engineering practice, you do not distinguish between open and closed sets. Therefore, it is unlikely that you run into this problem. Well, but well-postedness is nevertheless an important concept because it reminds you as an engineer to really clearly state what you're after. If you run an optimization problem like the one that was not properly bound, you're asking a stupid question, and therefore the optimization algorithm will give you a bad result. So the concept of well-postedness is a reminder that there's a very clear correspondence between the quality of your result that you get and the quality of the question that you ask. And a lot of work should be spent on formulating a good optimization problem. Let's talk about another important property, convexity. It can be a property of functions or entire optimization problems. But let's get started with the convexity of functions. On the left-hand side, you can see a convex objective function, but it could also represent a constraint function. And on the right-hand side, you can see a non-convex function with little wiggles. Mathematically speaking, convexity means that any function value on a line between x1 and x2, on a straight line between x1 and x2, has to be below the interpolation between those two function values. So let me draw a little graph, or a little sketch. Let's call this point x1 and this point x2. Then any straight line connecting these 2 points, well, just let's pretend that this is a straight line, would be above the function value, okay? And this expression on the right-hand side would just represent the u values on this line for a point between x1 and x2. And this has to hold for any choice of x1 and x2. And if this is given, then you call a function convex. And convexity is useful because if your objective function and your constraint functions are convex, then your optimization problem will be convex. And in this particular case, global minima are equal to local minima. So it's a nice way of knowing that you can stop looking for an even better solution because you're done. You won't get any better. Another important aspect of convexity is that you can access more efficient solvers if you know that your problem is convex, and these solvers will obtain better solutions in a shorter time. Another important property would be linearity of both functions and problems. So a linear objective function is shown here on the left-hand side, and on the right-hand side you can see a nonlinear objective function. Actually, a linearity is used in the literature in different ways. So when we say linear, what we mean is that you can express your function by this, okay? It does not mean affine linear, which would mean that we have to satisfy this formula here. We mean linear in a less strict sense, namely that we can represent our functions by this expression. And again, similarly to convexity, if your problem is linear, you can use different solvers that are made for this. They're more efficient. But now let's look at the criterion when your optimization problem is actually linear. When your objective function and your constraint functions are linear, then you do have a linear optimization problem. When your objective function is linear, but your constraint functions are not, you unfortunately still have a nonlinear optimization problem. And of course, when your objective function is nonlinear and your constraints are linear, it doesn't matter, you still have a nonlinear optimization problem. And when both your constraint functions and your objective function are linear, then you will end up with a nonlinear optimization problem too. So when we look again at the 2-bar truss problem, we can make an important observation concerning linearity. The 2-bar truss problem was a problem governed by linear system equations. And the response of the system is linear with respect to loads, for example. However, the objective function is nevertheless nonlinear with respect to design variables. So we do have a nonlinear optimization problem, although the system is itself, mechanically speaking, a linear system. So please carefully distinguish between linearity of or nonlinearity of the system equations and the corresponding optimization problem. Another important property of objective or constraint functions would be monotonicity. Monotonicity simply means that your function value increases or decreases upon increasing or decreasing your design variable value. So a linear function here would be a monotonous function, but also a hyperbola would be a monotonous function because it's always going uphill or downhill. Mathematically speaking, we can say that a function f of x is strictly monotonically increasing if this function value, where for the ith variable we use the value xaia, is larger than this function value, where we, for the ith design variable, use the value xib, and xia is larger than xib. So this would define monotonicity with respect to the ith variable. The same thing is true for monotonically decreasing, and there is a related notion of weakly monotonically increasing or decreasing if you replace the greater than or less than sign by a greater or equal or a lesser equal sign. Monotonicity does not mean that a function is linear, as you can tell by the hyperbola. However, linearity always implies monotonicity. So then there is another important distinction between continuous optimization problems and discrete optimization problems. Well, continuous optimization problems have access to the design space as a continuum, versus in discrete optimization problems, there are only particular designs available. And there are different algorithms available for discrete optimization problems. However, within this lecture, we only consider continuous problems and continuous methods. Let me finally comment on an important distinction between two types of optimization problems. Optimization problems with closed form solution and optimization problems that would have to be solved numerically. So for the two-bar truss that we intentionally chose for this to be possible, we can access the mapping from design variables to quantities of interest. The formula for quantities of interest is known. You can write it down like this and also study the behavior of quantities of interest upon changes of their design variables. For most realistic design problems or optimization problems, you do not have this available, but instead you have a kind of a black box solver, typically finite element code or a CFD simulation or something else that would provide the mapping from design variables to quantities of interest. And the optimization problems that we will look at, they are able to treat this as a black box. So that's important. That's an important property. So this would be it for today. We covered the fundamentals of optimization in this lecture in a very simplistic way. And in the lectures to come, we will scale that up to more complicated and more realistic optimization problems. Next week in lecture 3, we will start talking about high dimensionality. I see you then, and I wish you all the best and stay healthy. See you next week.